All right, hello everyone. My name is Andrew Wong, and that's my colleague Colin McCabe. We both work at Cloudera, and today we'll be speaking about in-memory caching HDFS, lower latency, same great taste. Let's start by thinking about some of the problems that might emerge in a modern Hadoop data warehouse. So here we have our Hadoop cluster on the right, and our data analyst, Alice, on the left. So what Alice is doing every day is basically making queries to this Hadoop cluster, and then waiting for a results test to come back. And she just does this over and over again every day. That's her job as a data analyst. But let's say that some new fresh data lands in the Hadoop cluster. And of course, Alice wants to query it. This is very common for time series data, for instance. But at the same time, there are also 100 other data analysts who also want to query that same fresh data. So what happens to that machine with the fresh data? Well, it's undergoing a whole lot of load and disk contention, and it falls over from an I/O contention point of view. Okay, let's look at a different situation too, where the same problem sort of emerges. Alice is this time just running her same query on the Hadoop cluster. But at the same time, a big roll-up job, which is querying over the full data set in the warehouse, also starts going. And it's just lighting up all disks on the cluster. So what happens to Alice's interactive query? Well, it comes back very slowly for the same reason. It suffers from disk contention when it's competing with this large roll-up query. So we have these two problems that we've identified when you're running these concurrent scenarios. The first of data hotspots, where everyone wants to query the same fresh data, and also the issue of mixed workloads, where we have both high throughput roll-up queries running alongside these latency-sensitive point queries from data analysts. In both situations, the same problem emerges, that of disk I/O contention. So how might we solve disk I/O contention? Oh, pretty simple, right? We should just cache it in memory. Memory is, of course, much faster throughput than disk, and it provides fast, random, and concurrent access. And it's often true that interesting working sets will fit in aggregate cluster memory. This holds up when you look at traces from Facebook's Hive cluster, for instance. Moreover, memory is becoming increasingly affordable. Moore's law is still holding true for memory density, and I looked on HP's website, list price, you can buy a 1 terabyte RAM server for about $40K, which is surprisingly affordable. So let's say we actually bought a bunch of these large memory servers and rerun like the same scenarios as before. Well, again, here we have Alice in her Hadoop cluster, and this time we have all this extra memory we're using for page cache on these machines, because we bought these high memory machines. When Alice makes a query to one of these machines, the data that the query is reading gets pulled into page cache. So now we have a hot page cache where the data resides, and then the results that comes back. But let's say Alice runs the exact same query again. An issue emerges, which is that when you rerun the query, there are actually 3 different replicas for this block in HDFS. So you're not guaranteed to hit that hot page cache. You might hit one of the 2 cold replicas instead. So this is one issue, but let's say we get lucky and we actually do hit that hot page cache replica. So Alice is hitting the hot page cache. But how about those large roll-up queries you just talked about, where it's just touching all the data in the cluster? Well, this large roll-up query will start sucking up page cache and essentially turn that hot page cache back into a cold one for Alice's data that she cares about. But let's ignore that even. See, Alice is running her query in isolation, and she's lucky with the placement. She hits that one hot replica. Even so, when you look at the HDFS reads that are going on in this scenario, you see that there are a bunch of extra copies happening when you look at the read path. Moreover, there's also this checksum verification going on, which is not strictly necessary if you're reading from cache data, because we have ECC RAM these days, so we could potentially skip this overhead. So all said, we have these design considerations that come up when you're thinking about caching. We have this first issue we talked about of placing tasks in memory locality, where we want to make sure we co-locate our tasks with hot cache. The issue of contention for page cache from other users. Think of that roll-up query, using up resources in the cluster at the same time Alice is making her small queries. And finally, the issue of extra copies when reading cache data, as well as the overhead of doing checksum verification. So each of these are addressed in HDFS caching. So for the first, we actually expose cache locations to application schedulers so they can place their tasks for cache locality. For the second, we will explicitly pin hot data sets in memory so they cannot be evicted when they're running concurrently with other large queries. And finally, we added a new zero-copy read API for reading cache data very efficiently. So this is the outline for the rest of the talk. We'll be talking about the implementation of HDFS caching on name node and data node side, as well as the zero-copy read API, and then going into an evaluation for HDFS caching with a series of micro benchmarks, MapReduce, and Impala benchmarks, and then concluding by talking about future work. Now I'll hand it over to Colin to talk about the implementation details.
Thanks, Andrew. Can you guys, is this on? Okay. So, our basic API here talks about what we call cache directives. Cache directive describes a file or a directory that should be cached. So basically it's done by path here. Cache directives also have what we call a cache replication factor, which can be, in between 1 or n, where n is the number of replicas. So we can cache all of the replicas that a block has, or we can cache only one. It's up to the directive to determine that. These cache directives are stored permanently on the name node, so they're part of the metadata that we are storing. We also have cache pools which provide access control and quotas, but we won't be covering that here. It's mainly sort of an admin thing. So let's talk about the architecture a little bit. So basically, we have our cluster with name nodes and data nodes here. And the DFS client says, we want you to cache foo. It sets up a cache directive on the name node. The name node can identify the blocks that make up the foo file. And then it can tell the data nodes that have those blocks to cache them. And it does this in the form of a reply to one of the data node heartbeats. So that's the mechanism we're using here. The data nodes, in turn, when they finish caching these blocks, will reply to the name node. They'll send a notification of that to the name node. So the name node can then become aware of that. It can become aware of where these blocks are cached. And so if another DFS client asks, where is foo cached, by calling get block locations, the name node can respond. So this makes possible the API we talked about earlier, where you can move the computation to the cache. Our cache is implemented using mlock. Basically, the data node pins these cache blocks into the page cache using mlock, and then checksums them. There are some advantages to this. One of them is that we don't have giant Java heaps, which generate long GCs. We can support zero copy and short circuit, which we'll talk about a little bit more later. And it's just generally advantageous. So now let's talk about the zero copy read API a little bit more. So we talked about extra copies earlier and how they're bad. I mean, they use up memory bandwidth, they use up CPU. So the zero copy read API allows us to avoid these. Essentially, it allows the client to map the cache replica into its own address space. So accessing that data becomes just as simple as doing a memory dereference, and then the kernel takes care of the rest. And this avoids the overhead of the read and preread system calls, which can be quite an overhead in some cases. Because we're going through the kernel and we're just using memory mapped I/O, we don't get a chance to do checksum verification with zero copy. So the implication here is that the zero copy read API can only be used on cache data, or when the application doesn't care about checksums. The application can choose to say, I don't want you to do checksums because I'll do them myself. So if we're going to get more concrete, these are the new methods which are in FS data input stream. And basically, other file systems besides HDFS could implement these. So far, HDFS is the only one, but they are generic. When you get a buffer back from this first read method, you need to release it later so that the data node knows that it can uncache this if necessary. So let's talk a little bit more about skipping checksums. As we said earlier, we'd really like to skip checksum verification when reading cache data because the data node has already done the checksums when it cached the block. And we trust memory because we believe that we probably have ECC memory. And in general, if you can't trust memory, you're kind of in a bad place because you're probably going to crash. So being able to skip checksum verification enables the more efficient SCR without checksums and ZCR, of course. So the requirements here is that the client needs to know that the replica is cached, And the data node needs to be able to notify the client if the replica becomes uncached. So remember that things can change here, right? New cache directives can be added, cache directives can go away. There's not a static view of the universe here, so we need to have some notification mechanism. So our solution to this problem is to use shared memory segments to communicate which blocks are cached between the data node and the DFS client. So this has some nice advantages. It's very low overhead, and it allows us to, for each read, we can actually determine this. I'll talk a little bit about that on the next slide. So we have sort of a protocol here where we have a region of the cache memory which is dedicated to a block. Let's say block 123. When the data node becomes aware that checksums can be skipped, it will actually set a bit in this shared memory that says you can skip checksums. Then the DFS client, in turn, when it actually starts using this block, it sets an in-use flag. So basically, this lets the data node know that it can't just uncache this. It has to wait for the client to actually be done, or else things won't be safe. So the client can then create a zero-copy map byte buffer, or of course it can do a no-checksum read. So when the data node becomes aware that when the data node wants to stop caching this block, basically it gets rid of that can skip checksums bit, and the DFS client notices that, and then it stops using that block, gets rid of the zero-copy map byte buffer, and eventually the in-use bit goes away. So this is sort of the protocol here. Let's summarize what we just talked about. The cache directive API provides per file control over what's cached. So this is a per file API. It's not parts of files and it's not parts of blocks at the moment. The name node tracks the cache blocks and coordinates the data node cache work and uncache work. The data nodes use mlock to lock the page cache blocks into memory. And the DFS client can determine whether it's safe to skip checksums via this shared memory segment. Caching makes it possible to use the efficient zero-copy API on cached data. So going back to our outline, the next thing we'd like to talk about is some single-node micro-benchmarks. So our test node had 48 gigabytes of RAM. We configured 38 of it for using with the HDFS cache. We had 11 SATA hard disks. We had two 4-core 2.2 gigahertz Westmere Xeon processors, and basically a 10 gigabit per second network there. But these are single-node benchmarks, so the network's not very relevant. So what we'd like to figure out is how much faster are cached and zero-copy reads. In order to do this, we created a program called vexsum, which computes the sums of a file of doubles. Basically, it just assumes that what it's looking at is a file which contains doubles, and it'll sum all them up, one after another. So very simple. We optimized it using SSC intrinsics. This is an Intel CPU thing, which is very fast. It's a libHDFS program, so we could use those aforementioned intrinsics. It allowed us to toggle between various read methods, so we can get the results that we're going to show you today. Just a note on terminology here. I guess I mentioned this a little bit earlier in the talk, but it bears going over. SCR is short-circuit reads, and ZCR is zero-copy reads. So the first thing we should look at is the throughput. The experiment we did here was reading this 1 gigabyte file 20x, and of course computing the checksums. Or not the checksums, but the sum of the doubles. TCP does the worst, which is kind of expected. TCP without checksums does slightly better. SCR gets sort of double, roughly, maybe a little bit more than double the performance of TCP. SCR with no checksums, of course, gets like half a gig per second better. And ZCR does the best, of course, getting around 6 gigabytes a second, which is getting close to memory bandwidth. Not quite at memory bandwidth, but getting close. So one interesting thing that we noticed is that we redid the experiment again. Instead of reading the same 20 gigabyte file, instead of reading the same 1 gigabyte file 20 times, we read a 20 gigabyte file one time. So in essence, this is comparing rereading the same thing 20 times, whereas reading something 20 times bigger once. And we found that ZCR actually did basically about half as well in the case of the 20 gigabyte file. Now, it's still faster. It's still faster than any other thing here. 2.7 is still faster than SCR. But you can see that there's a substantial advantage gained from reusing the M-maps. So what are the takeaways from here? Skipping checksums matters more when we're going faster. ZCR gets close to bus bandwidth at 6 gigs a second. And we need to reuse these client-side M-maps for maximum performance. Looking at this a little more closely, we saw that the page fault function was 1% when we were rereading the same 1 gigabyte file, and it was 18% when we were doing the 20 gigabyte file. So essentially what this means is that there's an overhead to setting up new M-maps, even when the data is in cache. That overhead still exists. So you gain a substantial advantage by reusing M-maps. But you also can see that there's an advantage to using ZCR even if you can't get this reuse. It's just a smaller advantage. So let's talk about CPU cycles, because that's another important dimension of performance. How much CPU are we leaving around for, doing actual work and not just HDFS? Here you see sort of the inverse of the previous slide. So more CPU consumed is worse. These results were gathered with the perf tool, which is a Linux kernel profiling thing. TCP and TCP with no checksums are sort of the worst. SCR is like roughly half that, and ZCR does the best here. So we wanted to know a little bit more about why ZCR was so much better than SCR here. It's basically just about half. So we made a flame graph of what was going on here. The SCR is the top, and the ZCR is the bottom here. What we noticed is that in the ZCR flame graph, this section is completely missing. And the section that I've highlighted here is the read system call. So you can see that the read system call actually takes kind of a lot of time and CPU cycles. So going into kernel space isn't free. It takes time. And pread is something that takes CPU. So the next result we did was sort of remote cache versus local uncached. And here's where the network comes into play. So given that we know zero copy is only possible for local cache data, we still have to ask, does caching provide a benefit when we're reading over the network? Or does it just not matter? Is it better to read from remote cache or local disk? So what these bars represent here, the first bar is basically, we did a TCP read of cache data. The second bar is iPerf, which is sort of the theoretical maximum you can get from the network. You can't go any faster than iPerf because that's sort of like the fastest you can transfer the data. The third bar is SCR, so basically SCR on uncached data. In other words, we're not reading from the cache, we're not reading from memory, we're reading from the disk. And we ensured that this was true by purging the page cache prior to running this experiment. And the fourth bar is DD, which is another sort of speed of light thing. Basically, DD will read from the disk as fast as it can, we assume. So what we see here is that we get pretty close to our theoretical maxima here. And to summarize, short-circuit reads need much less CPU than TCP reads. ZCR is even more efficient because it avoids that copy, hence the name. ZCR goes much faster when rereading the same data because it can avoid these page faults. And network and disk may be the bottleneck for remote or uncached reads. So you still need to figure out, what's the speed of your network, what's the speed of your disk, and that will shape your results. So next, Andrew's going to talk a little bit about some higher-level benchmarks in MapReduce and Impala.
Thanks, Colin. So for MapReduce, we evaluated with some jobs from the example MapReduce jar. We chose to use word count and grep. And we're using a 5-node cluster with the same hardware configuration as that of in a single-node test, where we had 40 gigabytes of RAM total, 38 of that allocated for HDFS cache in every data node, and 11 disks per data node. Our corpus here was a 17 gigabyte Wikipedia text dump. This is important because 17 gigabytes is small to fit into the page cache at 3x replication, which is important for comparing page cache versus HDFS caching. And here we ran each job 10 times and took the average. So let's look at word count and grep on cached and not cached data. So here I've split up each bar into the map and the reduce phase, where the bottom is the map phase and the top is the reduce phase. And the number here represents the amount of time spent in the map phase. And we're comparing these two jobs on uncached versus, on page cache versus HDFS caching. So the first thing you might notice, though, is that there's almost no speed up when you look at not using HDFS caching and using HDFS caching. And that's because these jobs are simply not I/O bound. Looking at word count, we're going at an aggregate 60 megasecond across our 4 nodes, and for grep, 330 megasecond across our 4 nodes. And this doesn't even compare well with just using disk, because after all, with 11 disks per machine, 4 machines, 100 megabytes of throughput per disk, you expect something like 4,400 megabytes a second of aggregate throughput. But here again, we're not coming close to even that, or much less memory. So, and then latency here barely changes because these jobs are not I/O bound. And we're looking at this more deeply, and we found out this is because of things like long JVM startup and MapReduce initialization time. There are also many copies in text input format, and it does not use the new zero-copy read API we added. Finally, for reduce-heavy jobs or shuffle-heavy jobs, caching input data doesn't really help. So this is why we focus on just the map phase. But because these results were somewhat disappointing, we decided to try writing our own optimized MapReduce job to see if we could find some benefit. And that's byte count. So byte count is basically a trivial version of word count, where instead of counting the number of words in a file, it's counting the number of different byte occurrences in a file. And each mapper processes an entire HDFS block via the zero-copy read API. Meaning we have no additional copies in record reader or the input format between ZCR and the map function. There's no record swap required across block boundaries, so all reads are coming through the zero-copy read API. And we spent some time optimizing the inner loop using primitives rather than a hash map or objects, so it goes pretty fast. Overall, byte count is a very unrealistic job for the reasons stated, but we're hoping that sort of serves as a best case for MapReduce. And we also tried running byte count with a 2 gigabyte block size in HDFS to try and amortize MapReduce map task startup overheads. So what do these numbers look like? I left grep on the left side as our baseline comparison, and then we have byte count running on the 128 megabyte block size, then byte count running on the 2 gigabyte block size. And we see that we actually do get some speed up when you compare these two bars. We're going 1.3x faster when it's disk versus HDFS caching. But even so, looking at the aggregate throughput we're getting across our 4 machines, we're only going at half a gig. So not very impressive when you think about memory speeds. So what's our conclusion after having written this very optimized MapReduce job? We think that most MapReduce jobs will see marginal improvement for reasons like startup costs for the JVM and CPU inefficiencies in the input formats and record reader. And also, if your jobs are very heavy on the shuffle and reduce steps, you won't see a benefit from caching your input data. Our optimized byte count job only saw modest gains, nothing close to what you might expect in terms of memory speed. And I think that overall, there needs to be more work done in MapReduce to take full advantage of HDFS caching. So let's move on to a set of Impala benchmarks. So Impala is an open source OLAP database developed by Cloudera, and all tests here were done with Impala 1.3, which is in the CDH5, using the same 4 data node cluster as in the previous section. So 4 data nodes, 38 gigabytes of the 48 gigabytes on every machine configured as HDFS cache, 152 in aggregate, and 11 disks per machine. So the queries we were running were all some variant of count star on a 1 terabyte TPC-DS store sales table in text format. This might seem to be a slightly weird configuration using text rather than more optimized formats such as Parquet or ORC. But the idea here is that running count star on text actually forces Impala to scan through all the data, making it a more fair comparison with our earlier MapReduce benchmarks. We chose to run 3 different scenarios. One was a 51 gigabyte small query, which is approximately 1/3 of cache capacity. This lets us compare against using page cache when we're at 3x replicates. Also a 148 big query, which is approximately aggregate cache size. And then try running that 51 gigabyte small query alongside a concurrent query scanning over the entire rest of the store sales table, a concurrent workload. We tested each of these in both cold and hot scenarios, where cold meant we ran echo 3 into Proxys VM drop caches to flush out page cache. And this essentially allows us to compare HDFS caching against just using page cache. So let's look at the small query results. So the first thing that I'm happy to say is that we're actually I/O bound. Looking at uncached cold, which means we're coming from disk, Impala achieves 2.5 gigabytes of throughput. So not quite our 4.4 gigabytes of theoretical optimum, but not too bad, not too far off. Moreover, on cached hot, we're getting 17 gigabytes in aggregate. So again, not like theoretically optimal, but not bad either. We're definitely going at memory speed now. Comparing uncached cold and cached cold, this is essentially looking at disk versus memory. Again, this is uncached cold means we're coming from disk to drop the page caches, while cached cold means we again drop page caches, but because the blocks are pinned in memory, they don't get uncached. So we go 3.x faster, which is basically the difference between coming from disk and coming from memory for Impala. Not a bad improvement. But looking at uncached hot and cached hot, for uncached hot, since we repeated this query a couple times, page cache got populated. So this is essentially comparing the efficiency of the short circuit read path versus the zero copy read path. And we see the same result that Colin found in the micro benchmark section still holds true, where we're going 1.3x faster when we're using ZCR, because it wins on CPU efficiency. Cool. Let's move on to the BigQuery. We didn't have the same 4 bars, but they look a bit different. This time, looking at the disk versus memory bars, uncached cold versus cached cold, we're going 4.2x faster, basically the same result. But for the uncached hot and cached hot bars, we see that we're going 4.3x faster. And remember before, these are pretty comparable. But this time, because the query's working set is much bigger, page cache suffers because it cannot schedule its tasks for cache locality. So we win when the working set approaches the size of aggregate memory. Let's look at the small query running alongside the big query, the concurrent workload. So here we're showing the latency of the small query in the uncached scenario, the cached scenario, and then as a baseline, the same bar from before where we're running that query in isolation. So we see that we're 7x faster when you cache the working set of the small query when it's competing with the big query. And this is, I think, a pretty cool result. It's just that caching has a lot of benefits when you're running these concurrent workloads. We see that the cached concurrent bar is, though, also 2x slower than the cached small query running in isolation. And this is because of CPU contention. Because we're running alongside one other query, we have half the number of CPUs on the cluster, even if I/O is essentially free because we're using zero copy. So we go exactly half the speed, which is a great result, too. So in conclusion, we've shown that for Impala, HDFS cache is faster in either reading from disk or coming from page cache, and that zero copy is more efficient than SCR in a real-world scenario. We see big improvements when we have a working set which is approaching the size of cluster memory. Remember the small query versus the big query, because Impala can actually schedule its tasks for cache locality when we use HDFS caching. Moreover, we're significantly better for these concurrent workloads. That's 7x speed up when that small query is contending with a large background query. Impala performance will also only improve. They haven't spent significant time doing CPU optimization, so I expect the differences between uncached and cached to only broaden over time as they start putting these things in place. With that, let's talk about future work for HDFS caching. So the number one thing we want to work on is some form of automatic cache replacement. Right now, users have to explicitly cache and uncache certain paths manually. And many users do not want to do this. It's too much overhead. So something like LRU or LFU is vastly preferable. But once you're doing automatic cache replacement, you might also want subblock caching. Oftentimes, for these columnar data formats, you're actually only reading a couple columns out of your entire table. So you only want to cache, let's say, a small byte range out of your entire Parquet file. And this is why we need subblock caching. When it comes to compression, encryption, and serialization, it's hard to do zero copy reads in these situations. So we need a better story there, I would say. But something I'm also really excited about is the idea of right-side caching, or in-memory only replicas. Once we have this in HDFS, it enables something like Spark RDDs for all HDFS applications, which will really help bring the benefits of in-memory to Hadoop. So in conclusion, we've shown that I/O contention is a real problem for concurrent workloads in modern data warehouses. With HDFS caching, we can now explicitly pin important working sets into cluster memory. And after that, applications can then place their tasks for cache locality. Once placed for cache locality, they can use the new zero-copy read API to see significant improvements in read performance. And we showed that we can achieve great performance through our micro benchmarks and macro benchmarks, where we saw that we could get 6 gigabytes a second for a single thread micro benchmark and 7x improvement for a concurrent Impala workload. Thank you very much. Any questions? Andy.
Hey, so I have possibly 2 related questions. So first, it's really great work. So what happens if the aggregate of the cache directives exceeds the amount of available RAM on the data node pool?
So we cannot cache more than the aggregate cluster memory size. Yeah. So we just stop caching at that point once we fill up. We have quotas on cache pools, so ideally administrators will actually configure their pools such that they do not all in aggregate exceed cluster memory size, and thus we avoid this problem.
Okay, so the second is for the related work that we talked about doing LRU.
Yep.
For LRU, is that actually on deck, or is that just aspirational?
So I feel that early customers are sophisticated enough to, again, go in and manually specify cache this, uncache this, but many users are not. So if we want to get HDFS caching out there in the hands of many different users, we're going to need to have automatic cache replacement. It's a high priority for at least myself and Colin in terms of what we want to work on for future work.
Yeah, okay. I guess related to that, have you thought at all about how you would invalidate references?
Sorry, could you repeat that?
How you would invalidate references to zero
So,
copy block buffers once expired?
that's a good question, and it's something that we already do. It's already an issue, right? Because I can change what the cache directives are, and the way that this works is that we have to keep checksums. We have to keep the data cached as long as people are reading something in a no checksum fashion. So a malicious client could grab onto that block and just hold on to it for a while. But eventually we'll time out the client, and basically we'll forcibly uncache it. So we have a timeout, which will be like a few minutes. And if clients choose to hang on to it for longer than that, then we won't guarantee that they'll get correct results, right? So.
Yeah, I was thinking more like in the case of a cooperative client, like for example, wanted to remove the HDFS block cache and do caching directly with the HDFS facility, and then of course be reliant on any LRU you might have on the HDFS side. How does that cooperatively work for the client that wants to operate like that?
That's an interesting question, and it's something that requires sub-block caching, because the granularity of the HBase block cache, as I understand it, is more on the order of kilobytes than on the megabyte order. So we would need to do this sub-block thing before we could start thinking about that. But it is an interesting question. Like, could we potentially hang on to these things for even longer than a few minutes if we had some assurances from the client? And I don't know. Might have to think about that a little bit more.
Sanjay.
Yeah, so common question. So even though you kind of say that comparing with the Rotex 5 that you did from Balas, gave you a fair comparison with your MapReduce. In a sense, it's an unfair comparison with anybody using either Impala or Stinger, because in almost all those situations you don't use a smart Python like Parquet or right? And like you're going to mention in conclusion that they all benefit from the fact that they read very good. So what would be really good, they read very good, okay? And what would be good is that if you do a Impala comparison with Parquet and see that given that Parquet and Impala read very little, what is the benefit of the cache?
Well, maybe I can answer this question. So essentially the question is this a fair comparison? Because maybe we can use Parquet or another input format which is more optimized. Is that a good summary? Okay. So, I mean, basically our results show that MR just doesn't spend much time in I.O. So if you had an infinitely efficient format that spent no time in I.O., is that really going to help MapReduce if MapReduce doesn't spend time there? I would say that a lot of these quote-unquote efficient formats, if they're compressed, for example, what we're doing is we're trading CPU for reduced I.O. time. But given that we're not I.O. bound, CPU is what we don't have a lot of. So we shouldn't trade something that we have a shortage of, which is CPU time in MapReduce, for something that we have a surfeit of, which is I.O. bandwidth, right? At least that's my take on it. It would be interesting to run these results and see what we could get, but I'm not optimistic that that would change the balance of things.
Parquet and Hope actually the other advantage is the fact that it's less data on disk. So the compression of the disk is a benefit, and also the fact that your indexes and things that you avoid really skipping compilation. This is a longer debate. So my other question was on checksums. So one of the things that we are considering right now in HDFS is to move the checksums into the file as opposed to being offline. And if you want to move it inline into the file, or you're moving to the beginning of the file, like the guys at the KFS file system has done. Okay. If you move it inline, will it become, I mean, it's more of a question, do you think it'll be a workout for the fact that you are memory mapping the file and reading it, because now you can have the checksums intermingled and you won't get this contiguous application data?
Yeah,
that's
another good question. So basically, it's certainly true that if we mix the checksums and the data, that we couldn't do what we do now. I mean, right now you can get, like, let's say, a few megs of ZCR. ZCR wouldn't go away if we mixed the checksums and the data, but ZCR would be limited to smaller regions. So you would get less of a contiguous segment. And it's an interesting question. I know that Facebook did that work. They were talking about it a little bit yesterday. And they talked about it previously, to mix the checksums and the data. And that's another thing which, it will reduce the I.O. burden, right? Because we do fewer seeks in that case. But if the I.O. burden isn't really what's slowing down MapReduce, then I don't know. I don't know. It'll be interesting to see some results, to see what would speed up there, and what the bottom line would be. For Impala, it would be an interesting trade-off because we would potentially not be able to use ZCR in as many scenarios because we might need a minimum size for ZCR if we're reading like an entire structure. We want to be able to see that entire structure in memory. But on the other hand, of course, we'd get the improved I.O. efficiency of this mixing. So I don't know how those results would come in. Good question.
How different is lower HDFS caching from, let's say, Tachyon project? It's my first question, and the second question: when we can expect HDFS caching to be in the HDFS release, and will it be contributed back to one or?
Sure. Let's start with that. So this was actually already released in the Hadoop 2.3, and Hadoop 2.4 is going to be coming out, I think, very soon too, and it'll be in that as well. So it's already upstream in Apache. That's how we do things. When it comes to comparing with Tachyon, so we actually know the Tachyon guys pretty well. I'm from Berkeley, and HY is the main guy in Tachyon. I know him pretty well. So we sort of have different design goals, I would say. Tachyon is trying to be a layer on top of many different file systems. You might have HDFS, S3, Lustre, whatever, so on and so forth, all underneath Tachyon. And Tachyon is this common layer above it. But as a result, you have to run a separate set of services. You have to change all your applications and now use the Tachyon API rather than the HDFS API. And overall, we felt that there were still advantages to integrating these things directly with HDFS, especially when it comes to things like skipping checksums and being able to place things for cache locality. Again, we can do these transparent improvements for existing HDFS applications, which is not something you can do when you're using Tachyon. But they do address, I would say, sort of similar concerns. And that the point of Tachyon is to, for Spark REDs, move things off heap from Spark and also enable sharing. And these are two things that we can also do with HDFS caching. Good question.
The caching you do now is you say it's explicit caching, so you have to say cache this, cache that. Is there any plans to have like some kind of implicit caching schedule that does it for you?
So you could set up a cron job which just rolls over your cache directives periodically on a daily basis. So you load new data, you remove your cache directive for the previous day, you cache the new day. That's something that's very possible to do. There is also the question of, like I said, automatic cache replacement, which will satisfy some of these concerns as well. Any more questions? All right, thank you.